So using sigma notation to evaluate this expression, the first thing I want to do is I want to take the expression and make sure that everything is multiplied out as much as possible. It's nice to have some individual terms to work with so I can apply some of my theorems. So I start by taking that I plus 5 and multiplying it times itself since it's squared. When I FOIL all that out, I should get I squared plus 10I plus 25. At this point, with what I know about my I theorems and how sigma notation gets applied to all of these terms with these i's in there, I can take those theorems, like the theorem for I squared, that would be n times n plus 1 times 2n plus 1 all over 6. In this case, my n would be 18. So I would have 18 times 18 plus 1 times 2 times 18 plus 1 all over 6. Next, I would add. I have 10 times I, so I take my theorem for I, which is n times n plus 1 over 2. Again, n is 18, so it's 18 times 18 plus 1 all over 2. I am multiplying this by 10 because of the 10 in front of the I. Then finally, this constant term of 25, I take that 25, and my rule with the constant is multiply it by n, so I multiply 25 by 18. I have everything set up now to do my calculation. So after calculating for each part, I get my answer of 4,269. Next, we want to discuss how to find the exact area beneath the curve y equals x squared plus 5 on the interval from -2 to 3, assuming that this region is above the x-axis. To find this exact area, we're going to use the setup for the limit of a Riemann sum. In building this limit, we start by figuring out what delta x is. Figure out delta x, we take where the interval ends, we subtract where the interval begins, and we divide that by n. So our delta x is 5 over n. Now we start substituting in to our limit for a Riemann sum. We know what delta x is. We know that's 5 over n. A represents where this interval starts, so a would be -2. If we substitute all that in to our form here, that would be our form for our initial step to help us find this limit of a Riemann sum, which ultimately will give us our exact area. Now, as we go through and attempt to evaluate this piece by piece, you want to start by plugging into your function this expression of -2 plus 5 over ni. So we go back to our function, we replace our x's, in this case just the one that is being squared, with the -2 plus 5 over ni. If we write that out, all the other notation stays in place because we're not ready to use it yet. We'll use that notation once we've done all of our simplification and our algebra. So substituting in for the x, we have -2 plus 5 over ni as a quantity squared, since the x is being squared. We add on the 5, since we're plugging into this function. All of this right here represents that function value once we've substituted in for x. Remember, though, we still need to multiply on the 5 over n at the end. Next thing we want to do, continuing our algebra theme, we want to expand out this binomial square. So I might do a little scratch work here off to the side. I'm going to take negative 2 plus 5 over ni. I'm going to multiply that times itself. If I FOIL all that out, negative 2 times negative 2 get positive 4. My outside terms of negative 2 and 5 over ni, if I multiply that together, I get minus 10 over ni. Inside terms will be the same. And then when I multiply my last terms, I've got 5 over ni, basically times itself. That'll be plus 25 over n squared I squared. Collecting your like terms, you've got a pair of i's right there in the middle. You've got 4 and be minus 20 over ni plus 25 over n squared I squared. So what I have right here, I can now bring back to this part right here. And as I replace this part with what I just got, I'm understanding, because of the way the function was set up, I need to add on a 5 at the same time. So carrying over my work now to this next page. I'm trying to find my exact area. I'm still applying my limit. I'm still applying the sigma notation. And now I'm carrying over my work that I just found down here, understanding that I'm adding a 5 on to that work. So if I add a 5 on, collecting my like terms with that 4, I'm going to have 9 minus 20 over ni plus 25 over n squared I squared. All of that, remember, is being multiplied to this 5 over n, our original delta x. So all of this is scratch work down here. Up here I'm just continuing now with my process to find the area. So in my next step, a little more algebra to do. I need to distribute that delta x idea through, so I need to distribute the 5 over n. As I multiply this through, multiplying to the 9 in front, I would have 45 over n. Multiplying to the negative 20 over ni, I would have negative 100 over n squared, because it's n times n, and then that I. Now as I distribute to this 25 over n squared I squared, I'd have 5 times 25, which would be 125 over n times n squared, which would be n cubed, and then I squared. So I've done a whole lot of algebra to this point, but finally I'm ready to do something about this sigma notation. Because if I apply this sigma notation now to each of these terms I've set up, I can start incorporating some of the I theorems that I know. Next step, area is going to equal, still not ready to deal with the limit. So that stays. The sigma notation drops out because I know that 45 over n represents a constant. So I can multiply that by n, according to what I know about my I theorems. For my next term here, I've got minus 100 over n squared. I'm going to multiply that to the theorem I know for I. That expanded theorem is n squared plus n over 2. For this last guy here, I've got plus 125 over n cubed. If I consider the theorem for I squared, the expanded form of that theorem is 2n cubed plus 3n squared plus n over 6. So I'll multiply that on to the 125 over n cubed. All right, we're almost to the finish here. to get to the finish, we're ready to apply our limit now. And we apply our limit as we do the calculating. In doing the calculating, notice with 45 over n times n, the n's will cancel. So if I set up my area as my next step here, so I'm going to have to spill over to the next page. Area is going to equal, we canceled out the n's, so I've got a 45 so far. Next little piece to evaluate here, I am subtracting. Okay, the quick little calculation to do here, because we understand how all these n's are going to cancel out. I'm going to take this 100 and divide by 2. That's all I have to do to evaluate this portion. If I take that 100 and divide by 2, obviously I get 50, so I'm subtracting that on. And then finally, for this last piece, the quick calculation I can do, because again, I understand how these n's are going to cancel out. I'm going to take 125, multiply to 2, divide that by 6. If I take 125 and multiply that to 2, I get 250. I put that over 6. I'm adding that on. So now I've got my numbers I need to calculate. I can figure out my exact area. If I round off to say a couple of decimal places, my exact area would be 36.67. And we don't have a unit of measurement to work with here, so we could just say U for units squared. I would say at this point we're celebrating just to get the number, so the units of measurement's optional.